Hey everyone, welcome back. I bring you the latest breakthroughs in physics and science, backed by deep research and documentation. If you love discoveries that push the limits, this is the place. Let's dive in. Imagine this. For decades, quantum computing had one rule nobody could break. Photons, particles of light, just don't talk to each other. This tiny detail blocked the dream of computers that run entirely on light, a wall that seemed impossible to climb. But now, scientists have cracked it. Using a single trapped atom, they've forced photons to interact, unlocking the secret to a universal quantum gate. This is more than a step forward. It's a total revolution in how we can build quantum machines. In this video, I'll break down exactly how physicists at the Max Planck Institute pulled off the impossible, explain what a universal quantum gate really is, and show why this discovery could finally unleash the full power of light. So, why is this such a game changer? First, you have to understand the paradox of the photon. Photons, the particles that make up light, are almost the perfect messengers for quantum information. They travel at the speed of light, the universe's ultimate speed limit, and they barely interact with their surroundings. This means they can carry delicate quantum states through fiber optic cables over huge distances without the info getting scrambled, making them ideal for a future quantum internet. But here's the catch, and it's a big one. The very thing that makes photons great for communication makes them terrible for computation. To compute, particles need to interact. They have to influence each other. Think of the transistors in your phone. They're just tiny switches controlling the flow of electricity to perform calculations. But photons, they naturally ignore each other completely. If you shine two laser beams at each other, they just pass right through. It's like they're ghosts. This has been the Great Wall standing in the way of light-based quantum computing. How can you possibly build a computer out of particles that refuse to talk to each other? For years, scientists tried probabilistic tricks that only worked a tiny fraction of the time. Not exactly reliable. To build a real computer, you need a process that's deterministic, meaning it has to work every single time. And for a long time, doing that with photons seemed impossible. So if photons refuse to talk to each other, how do you force them? You bring in a mediator, a quantum matchmaker. This is the heart of the breakthrough from the team at the Max Planck Institute, led by Gerhard Rempe. They came up with a brilliantly clever solution. Trap a single atom between two tiny, superreflective mirrors. This setup is called an optical cavity, and it's like a quantum echo chamber. The mirrors are so close and so reflective that a photon can bounce between them over and over, dramatically increasing its chance of interacting with that single atom in the middle. The atom is the key. It becomes the go-between that lets two different photons have a conversation, one after the other. Here's the basic idea. The atom has a quantum property called spin, which you can imagine as a tiny magnet that points up or down. A photon has a property called polarization. The genius here is that a photon's interaction with the atom depends on both the atom's spin and the photon's polarization. When the first photon enters the cavity, it can flip the atom's spin, but only if it has the right polarization. The photon then leaves, but the atom remembers the interaction. It's now in a different state. So when the second photon arrives, its own interaction is completely different because the atom has been changed. The atom effectively relays a message from the first photon to the second. This controlled, mediated conversation is the basis of a quantum gate. Just like logic gates are the building blocks of your computer, quantum gates are the building blocks of quantum computers. But this isn't just any old gate. It's a universal quantum gate, which is like a Swiss Army knife for quantum algorithms. With it, you can build any quantum operation you can dream of. This single atom became the key to creating a deterministic, universal quantum gate for photons, a holy grail for optical computing. Okay, let's get into how this thing actually works. The experiment itself is incredibly precise. The team uses lasers to cool and trap a single rubidium atom, holding it perfectly still between the two mirrors. Then they fire single photons at it, one by one. In one of their key experiments, they demonstrated a CNOT gate, which is short for controlled NOT. It's a fundamental operation. If the first qubit, the control, is a 1, it flips the second qubit, the target. If the control is a 0, it does nothing to the target. To pull this off, the first control photon goes in. If it has one type of polarization, it interacts with the atom and flips its spin. If it has the other type, it doesn't. The photon then reflects away and is stored in a coiled optical fiber over a kilometer long, just to buy the scientists some time. Then, the second target photon is sent in. How it reflects now depends entirely on the state of the atom, which, remember, holds the information from the first photon. This transfers information from the atom back to the second photon. But here's the crucial part. The whole process is bidirectional. Information can even be transferred back to the first photon. After the second photon is done, a measurement is made on the atom. Based on that measurement, a final, tiny tweak is made to the first photon still waiting in its fiber loop. That last step is what makes the gate's operation deterministic. It works with certainty, not by chance. In another experiment, they used the same setup to create entanglement. They sent in two photons and, through the same mediated process, caused their quantum states to become linked. A spooky connection that's an absolutely essential ingredient for the power of quantum computers. They had not only taught photons to perform logic, but also to form the deep connections that make quantum computing so powerful. Okay, so scientists made two photons talk using an atom. Big deal, right? The implications are massive. As director Gerhard Rempe stated, this quantum gate is a key element for an optical quantum computer. It solves a foundational problem. The biggest advantage is the potential for seamless quantum information processing. In many other quantum computers, the qubits that do the calculations, like trapped ions, are different from the particles used for communication. This means information has to be converted back and forth, and each conversion is inefficient and a major source of errors. A computer built with these photonic gates could eliminate that problem. The information can stay as photons the whole time, for both computation and communication. This opens the door to creating vast, distributed quantum computers linked by the fiber optic cables we already have, essentially building a quantum internet. Plus, many photonic systems have the potential to operate at room temperature. Now, to be clear, this specific setup with the atom still needs laser cooling. But the dream is to build on this and reduce the need for the massive, deep space temperature refrigerators used by many other quantum computers. This is why some projections see the market for photonic quantum computers growing to over $1 billion by 2030. You could call this the transistor moment for photonic quantum computing. The universal gate is that fundamental building block. The question is no longer, is it possible? But how do we scale it? Now let's be real. A single gate doesn't make a quantum computer. The researchers themselves knew their achievement was monumental, but the journey was far from over. Gerhard Rempe noted that it would be some time before a computer like this could outperform a regular one, mainly because the gate needs to be more reliable or have a higher fidelity. Even tiny error rates can cascade and ruin a complex calculation, and science never stands still. Since this foundational work, researchers have been exploring new ways to achieve similar goals. Some recent proposals use a principle called quantum indistinguishability to make photons interact without them ever needing to be in the same place. Other groups are making progress using different methods, like quantum walks, to create universal gates.